like, let's say my, actually, I got to hit this buffer button and I'm like, it's in my brain. Let me wait for the buffer. Oh my gosh. Like, let's say, all right, and let me get back to you so I can see you. Right. So we're going to have something that looks like this, right? Let's say some function. I don't know what kind of wave you're doing, but let's just say, let's start
I
with,
think he assumes it's a light wave because it's through a slit.
okay, a light wave. So then you're probably talking about an electric field wave, right?
I think so. Yeah, because it would be E.
Okay, yeah, all right. And so let me think. Let's just do I'm going to do a variation of this where the electric field varies in time. Okay.
Okay.
The electric field is a function of time. Now, a wave would be x and t, right? So, well, maybe let's start there just so you can understand.
Yeah, that's what we're used to.
There's going to be some amplitude, E max. And then are you guys using sines or cosines usually? Sine, right?
Fine, yeah.
Let's just say it's this. Are you okay with that?
Yeah.
Right.
And
oh, actually, let's say it's let's say it's a function of z, right? So
okay.
why I'm doing that? Let's imagine what this looks like. A lot of times when we're looking at this one, we say that this is x, this is y. What's this direction? Is it z or negative z?
Be negative z, right? Right hand rule.
All right.
X, y.
In that case, let's flip it. X.
And would it be k hat on the equation?
What's that?
Would it be k hat on the equation?
What's that?
Or is it, on the equation you put I hat? Would it be k hat?
Well, I guess
It doesn't matter.
Okay, you want to do it that way?
No, because you put z, so.
Well, this is the worst live stream ever, but the idea here is those symbols that we choose, these three symbols depend on the coordinate system.
Oh, okay. Okay.
Right? So
I see what you're saying.
This way, x, y, and z, so that it's standard, right? And let's say we want the electric field to oscillate about the, right? So as we travel along the y direction, we might see the electric field go up and down here. So this would be ky, and this would be in the k hat. And by
yes.
that, I mean the electric field would look like nothing here, then it would go up. And so as we go along the y-axis, is this becoming more familiar now?
Yeah, I remember this now.
There's my sine function. So the idea here is the electric field is directed up and down, which on this coordinate system happens to be the z-axis.
Okay.
As I move along the y-axis, the size of the electric field arrow varies. That's why it's k hat here. That's the way it points. This is y for the position along the y-axis. So far, so good?
So k is the position of the electric field vector, and y is the direction it propagates?
No.
Oh.
K is the direction the electric field is pointing. This wave is going to propagate. When you have a wave equation, this one tells you the propagation direction. So this is what's weird about it. The arrows themselves point up and down, but as this travels, isn't the wave going to move this way?
Yeah.
That's the y direction, agreed?
Yeah.
Whatever you see inside here helps you understand the propagation direction.
Okay.
That's why it's a function of y and time, right?
Okay, that makes sense.
So listen carefully now. The electric field up and down depends on y and t. or the electric field in the z direction depends on its yt coordinate. What time you look at it and how far from the origin you are. Good?
Okay. Yeah, good.
All right. So then you're trying to get the average of this, right? So here we're saying we want, well, have you talked about RMS?
No.
Root mean square? Before we do the math with calculus, I'm going to just draw it to remind you, right? So when you're doing a root mean square, we do the squaring first, then we take the average, and then you take the square root to finish it off. It's sort of like in matrix math, where you kind of work from this side out. You know what I mean?
Yeah.
All right. So if I square this wave, what's it going to look like? How is it going to differ?
The negative direction's gonna get flipped.
Yeah, and then do you agree the heights might change a little bit?
Yeah, bigger.
Well, it depends on whether they're bigger or less than 1, right?
Oh, right, yeah.
All right, so that's the squared wave. Now let's do this. Let me get a different color here. Mean. I'm going to take the average, okay?
Okay.
Now, you don't know this necessarily. That's the math part that we need to work out, but the average ends up being exactly this 1/2. So that's what you asked me about, but I'm trying to make you, right? This is the part that I'm hand waving that we will do in just a second, right?
Okay. Got it.
And then you take the square root of that. That's where we get a 1/√2. Remember all that RMS crap from circuits?
Yeah.
This is when I did this, and I could, yeah, okay. So the idea here is, well, wait a minute. I thought the intensity had a 1/2 in it. Well, remember, we see that we're going to find out this RMS is a way to average a periodic function. If we're going to average that periodic function, it turns out if you average this, the answer is 0. Agreed? Because I have as much above and below.
Yeah.
So in order to get a reasonable average, what we do is we first square it, then we average it. I'll show you that we get a 1/2. Then you take the square root to get back to the right units. Instead of having units of E squared, you have units of E. But the intensity depends on the amplitude, the average amplitude. This is the RMS. In a sense, that's like the average amplitude, so to speak. You know what I'm saying? Remember how amplitude and RMS were related by this 1/√2?
Yeah.
All right, so that means intensity equals or is proportional to amplitude squared, right?
Yeah.
And that's how we're going to get a 1/2 back.
Okay.
Got it?
Got it.
So now I would like to erase this bottom part.
Cool.
Is this helping you as well, Alan?
Yeah, I'm starting to see a relation.
Yeah. So let's just do this, right? Well, how do I get E squared? Isn't that really the same thing as E dot E?
Yeah. Yeah. Yeah.
Well, what's E dot E?
Just the magnitudes times the angle between them, which is just 1. So
Emax squared sine squared k hat dot k hat. What happened to the k hats?
you go to 1.
Do you agree that that's what we just did with the squaring it?
Yeah. Okay.
What's that?
I said yeah.
Because both of these are squared now, right?
Hmm.
All right. Now I need to average it. How do we average it, right? Well, let's think about this. What does an average mean,
Um,
right? Let's do like, let's say you have x1 right? That would be one way to get an average, right?
right.
You just add them up. But now we're trying to average a function, right?
Okay.
So now we need to get the function at height 1. So function at, and let me be clear here. We're going to have to get E max or E as a function of y and t at t0 at some later time. Right, we're going to average all these up and divide by
However many.
number of times, right?
Right.
It turns out if we think carefully and work this out in calculus land, this is equivalent to some kind of sum. Makes you think of an integral, doesn't it?
Yeah.
Right? And now think about this. Do you agree that the average over one period should be the same as the average over many periods? Shouldn't it be the same?
Yeah.
Yeah.
Mhm.
So let's just do this. Let's say we go all the way up to our final one should occur at the period, right?
Correct. Yeah.
So now think about this. How many times are we going to get? Well, the number of times should be the period divided by n, where n is the number of times I use, right? Or sorry, divided by, excuse me, dt, the time increment I use.
Okay.
If you take, right, if you take the period and split it up into second intervals, that'll tell you how many.
Okay. Yeah.
Right, so as we let dt get smaller and smaller, I could flip this to the top. Do you see you get an integral over dt? Because the sum is the integral, right?
Right.
So here's what we get. And I guess that whole time I should have been writing e squares, right?
Oh yeah.
Average, to get the average, this is what we're going to do. So e squared average is equal to 1 over the period times the integral over a period. Oops. Right?
Yeah.
Of the function. Now, it turns out the y coordinate doesn't really matter because we're going over a whole period. The whole function goes through the whole oscillation at every point in space in one period. I'm going to say that again.
Right.
You tell me a spot right there. If you wait one period, isn't it going to go through the whole spectrum of the ups and downs?
Yeah. Eventually.
And so with this one, right?
Hmm.
So with this one. So it turns out this particular integral, and only this particular integral, we could actually drop the function of y part.
Okay. That,
No matter what
Interesting.
value of y you choose, it's still going to give me the same result. So I could choose the point y equals 0 without loss of generality.
okay. That makes. Okay, I was wondering why he did that, so that makes sense. Yeah.
So we could set this to 0. We could set it to 17. You could choose any value you want. Well, why not choose 0 to make our life easier?
Okay.
What was this damn function? Emax squared sine squared. I'm going to choose to set y to 0 because it doesn't matter.
Right.
And then, well, take a look. I get a minus omega t here, right?
Mhm.
What's sine of minus omega t?
Sine of mine.
It's negative sine omega t.
Oh, and that just gets canceled out with a square. Okay.
When you square it, fuck it. I mean, French. Second meeting, oh, got something. I forgot I was live streaming. My bad. All right, whatever. So in this case, how do you agree this pops right out?
Mhm. So we're just integrating sine squared.
So let me just rewrite this up here. I'm running out of room. Is this what you wanted to know?
Yeah.
Thank God.
Yeah, I know. This confused me. Like,
well, if it's not, too bad, I'm leaving.
yeah, so this made it clear because Mr. Youngblood just introduced it and explained why, but I was like,
Yeah,
yeah,
got it?
got
What's
that.
sine squared? How do you integrate sine squared dt?
He was telling us to do as an exercise. He was saying try using integration by parts because it's gonna help us later, like the technique, the way to do it by integration by parts. But when I first did, I tried using an identity, a trig identity.
Yeah, like the double angle, right? What is
Yeah.
it? What is it?
Let me see. 1/2 cos. Wait, 1 minus cosine. Oh, 2 omega t.
Got it?
Yeah, and then that's pretty simple.
Help me out. Hook a brother up. What's omega in terms of period?
2 pi over the period.
Thank God you remember that, or I would have killed you. All right. Do you agree you can plug this, and do this, and the answer
Yeah.
is gonna be?
1/2.
How can you tell? Right? There's a 1/2 right here. So what you're telling me is this term is going to drop to 0. Do you agree? That's what you.
Oh yeah.
Right? Otherwise, because the 1/2 is going to give me the 1/2.
Right.
Right? The dt gives you the period, which cancels there. So the 1/2 works. Why does this one go to 0?
Does it have to do with the nature of cosine?
Okay, give me more.
Um.
What could I do to prove it to you without doing any math?
Oh, is it because it's? Oh, I was gonna say because it's an even function. Oh wait, yeah, because is cosine even or odd? Because you're doing 0 to t and they're
Wrong
symmetrical.
words, wrong words. Not even or odd, but periodic.
Okay.
That's why I called this video periodic, right?
Okay.
I'm going to draw something for you, right?
Mm-hmm.
If this is the period, right? Sine looks like this.
You might want to move to the right a little bit.
Sine of twice as fast, what does it do? Oh boy. That's cosine of twice as fast, right?
Right.
And I'm sorry, my picture's kind of sloppy there. Let's tighten that up a little.
It's also going a little off the screen. I don't know if it's going to be.
Shoot. Thank you. Better?
Yeah.
Do you agree this function here is sine of omega t?
Yeah.
This one up here is cosine of 2 omega t, twice as fast, 2 oscillations.
Right.
What does an integral mean?
Area under the curve. So, okay.
See what I'm saying?
Mm-hmm. It's just going to go to 0. That makes sense.
This and this cancel those two. 0. You get 1/2. You good?
Got it. Yeah. Thank you so much.
Yeah. All right. You know where this is. If somebody needs to share it with